All right. Um, Hello, class. Good afternoon. Um, hey, let me tell you something I've observed. Maybe you've observed this as well. Um, you know how only essential businesses are supposed to be operating right now? Did you guys notice that lawn care is considered to be an essential business? Um, I swear, I've seen more people mowing lawns than I ever have before. So I don't know, maybe you guys are having the same observation. Um, Another thing is, I think I've only seen people over 70 at grocery stores. There's a lot of people who should be at home who are not at home. All right. Uh, Today we're learning about the um, more about capacitors. Okay. So, hi everybody. Let's see. Hi Rourke. Hi Rowan. Hi Mina. Hi Zach. Hey Aisha. Hey James. Hey Alex. And hey Alex. Hey Alexes. Um, okay, so we're learning more about. Hi, Stephen. We're learning more about capacitors today. All right, and um, someone says Sprouts. Hi, Fu. Sprouts does delivery, so we don't go shopping anymore. Um, a third Alex, and looks like Justin is saying something I don't even understand what he's saying. Typical of Justin. Um, I went to Sprouts today, and they actually were pretty well stocked. So Sprouts seems to have enough produce. All right, rolling right into the lesson. Did you know that if you have two capacitors in series, like this, that it is equivalent to a single capacitor? So if you have two capacitors, C1 and C2, it is equivalent to a single capacitor, which we'll call C sub S. And unlike resistors, where you would just add these two together, capacitors are a little bit different. They're actually the reverse for from resistors. So capacitors, for series capacitors, they obey the same rule as parallel resistances. Okay, so it's the same formula for parallel resistances, but it's applied to capacitors. Okay, um, why is that? Well, you might remember that the formula for capacitance was epsilon A over D. Okay, and so if we look at this, we have a certain distance here, and we have a certain distance here. So we're kind of adding 1 over D together, so you get this formula. Or you have to add the distances together, which means inverting the capacitances to get D on the numerator. If you have two capacitors in parallel, that is equivalent to a single capacitor, which we will call C sub P. And C sub P is equal to simply C1 plus C2. So this is hopefully you've been able to notice here that it's the opposite rule from resistors. This is the rule for series resistors, but it's the rule for parallel capacitors. Okay, so it's flipped. So let's do a little example. Okay. Let me just draw a capacitor network. And let's say that these are this is 2 nanofarads, this is 1 nanofarad, this is 3 nanofarads, this is 4 nanofarads, and this is another 1 nanofarad capacitor. We want to know, what is this equivalent to? Okay, so the first thing I notice here is that I've got 3 capacitors in parallel. So I'm going to use this rule to add these capacitances up. So I have C sub P equals 3 plus 4 plus 1 equals 8 nanofarads. So these are equivalent to 8 nanofarads. So then I can redraw my circuit. Where I have 2 nanofarads, 1 nanofarad, and 8 nanofarads. Whoa, is Aisha bored with my lesson? She just gave a yawning emoji. Oh my gosh. I'm sorry, Aisha. I will make sure to make the next lesson a little bit more difficult for you so that you don't feel bored by it. Okay? Okay. So we've got 3 capacitors now that are in series. And so I'm going to combine them with the series rule for capacitors. So we have 1 over C sub S equals 1 over 2 plus 1 over 1 plus 1 over 8. Like that. So that is what? 0.5 plus 1 plus 0.125. That equals 1.625. And that's 1 over C sub S. All right, which I then have to invert. So let me invert that. 1 over 1.625 equals C sub S equals 0.62 nanofarads. Okay, so that means that this capacitor network is equivalent to a single 0.62 nanofarad capacitor. All right, so first thing you should know from this lesson is how to combine to simplify capacitor networks. The next thing I wanted to talk about is what would happen. Okay, so what if we start out with 2 capacitors that are in series? Okay, and let me just pick some numbers for these. Let's say 3 microfarads and 1 microfarad. Okay. And these capacitors start out with no charge, so neither plate has any net charge on them. Okay. And let's say that we attach a battery to this capacitor network. Okay. The battery is going to push positive charge onto this top capacitor plate, which is going to, in turn, push positive charge away from the bottom capacitor plate, which will leave behind negative charges. Okay? And then the positive charge that got pushed off is going to land on this plate. Okay? And that positive charge is going to push off more positive charge back into the battery. So you have negative charge here. Okay? So this is how the capacitors become charged. You have basically a chain reaction where extra charge is going to get put on one plate, which is going to make charge on the other plate move, which makes it go to another location, and then that charge is now on a plate, which pushes more charge around. So it's a chain reaction. It's like dominoes, okay? And so what we would like to know is how much. Ooh, there's some drama going on in this live chat. Wow. Interesting. I'm going to have to read through that later. Okay. So what we would like to know is how much voltage does the 3 microfarad get, and how much voltage does the 1 microfarad capacitor get. Okay, so that's what we're trying to figure out. Let's say that for simplicity, this is a 10-volt battery. So anyways, we're going to apply, first of all, we're going to apply Kirchhoff's voltage law to this circuit. So the change in, if we add up all the voltage changes around this loop, it has to equal 0. And what that says, we've got a 10-volt rise across the battery, and then we've got a drop across the first capacitor, the 3 microfarad capacitor, and then we've got a drop across the 1 microfarad capacitor. So the sum of those two drops has to be equal to this rise in order to satisfy Kirchhoff's voltage law. So that comes from KVL. All right. Another thing you should know about is if you start with two capacitors that are uncharged and they're in series, then the charges on those capacitors have to be equal. So the charge on the 3 microfarad capacitor is equal to the charge on the 1 microfarad capacitor. So why is that? Well, it's because, remember how I said they both started out uncharged and then we attached this battery. And so any charge that got kicked off the bottom plate here of this top capacitor gets pushed on to this plate of the bottom capacitor. So any charge that leaves this plate ends up on this plate, which means that they have to have the same charge, right? Because if 1 coulomb leaves and lands here, then this one will have a surplus of 1 coulomb, okay? So the charges have to be the same if they're in series. All right? So now we're going to use, so this is kind of an important observation. So anyways, now we're going to use the key equation for capacitors, which is Q equals CV, which means that we can write this equation right here as CV equals CV. Okay? Oops, that should be a 1 and a 1. So that means that 3 micros times V3 equals 1 micro times V1. Notice that the micros cancel out. So the fact that these were microfarads had no effect on what our answer is going to be. And so we just get that the voltage on the 1 microfarad capacitor is equal to 3 times the voltage on the 3 microfarad capacitor. So we can take this and plug it back in to V1. And so we get 10 equals V3 plus 3V3. Which means 10 equals 4V3, which means that 2.5 volts is how much potential difference the 3 microfarad capacitor has. Okay? And that, of course, immediately tells us that the remainder of the voltage is the 1 microfarad capacitor. So that means that V1 equals 7.5 volts. Okay? All right. So I've got some questions here that I'm going to answer before I sign off. It says, wait, so capacitors work kind of as resistors because their voltage drops? The answer to that question is yes, in a way. They do act like resistors. In fact, the general term for devices like this is what's called an impedance. Okay, so resistors provide impedance. Capacitors also provide impedance, so they sort of block current flow. And then there's another question. It says, technically, this has no resistors. It doesn't mean there's no voltage. Again, you have voltage between the capacitor plates because there's an electric field between the capacitor plates. Anytime there's an electric field, you have a potential difference according to that integral equation. If you remember, the potential difference is minus the integral of the electric field. So you can have potential difference without resistors. The equation V equals IR is simply telling you if you do have a resistor, it's an easy formula for the potential difference across that resistor. Okay? I don't know if anyone noticed my little painting of Bug right here. You guys see that? That's Bug. I would ask the class to raise their hand if they noticed it before, but I can't see you guys. So that's my lesson for today. I'll see you tomorrow. I hope you have a good rest of the day. Oh, by the way, let me show you some stuff. I'm reading this book. It's pretty good. You should check it out. And also, I got this the other day. So I don't know if anyone wants to play that with me. I don't even know how to play. All right. Have a good day. Bye.